Okay, welcome to BME 27, your first virtual BME 271 lecture. This one will be called Digital Filtering 1. And in this lecture we're going to be talking about filter analogies, that is analogies to digital low-pass and high-pass filters. And then we'll get into the nitty-gritty of digital low-pass filters. So why do we care about doing digital filtering? So previously, of course, we have talked about analog filters. We talked about analog low-pass filters, high-pass, band-pass, and band-reject filters. We talked about specific circuits for implementing those and how to build them, and then also what they do to our input signals, and how to actually come up with a given specification for one, given a certain task that we want to do with them. So why, if we have those tools already, why do we want digital filters at all? So one thing that digital filtering gives us is the ability to do much sharper filtering. That is, we can get much sharper roll-off with a digital filter than we can with a simple circuit implementing an analog filter. So specifically, cascading two analog filters will double the rate of roll-off, right? You can get a sharper transition by increasing the number of cascades that you have in your filtering circuit, but of course that doubles the electronics each time. So here's an example of where we to motivate this, in that with the blue curve here, this is the magnitude of the transfer function for one filter compared to the same filter cascaded 50 times. I also pushed the corner frequency out here a little bit, but you can see that with 50 filters we get a far sharper roll-off between the pass band and the stop band. But if we actually wanted to implement this in electronics, we'd have to build 50 filters. So, of course, it's much easier to implement 50 filters in code rather than in actual physical circuits. The other thing that digital filtering buys us is flexibility. So let's say that we want to change the characteristics of our filter. Well, it's a lot easier to change code and just recompile our code or rerun our code than it is to change circuits, right? In addition to that, if we can do most of our filtering on the computer, then we can now think about designing circuits to be sort of one-size-fits-all for multiple applications of a given circuit, and that means, of course, that you can reduce manufacturing costs and everything. And then you can just tailor the code to a specific application. So you can imagine that this overall saves both time and money when you're developing a given instrument. Okay, so now that we have motivated our discussion, let's move on to the first main topic, which is analogies of low-pass digital and high-pass digital filters with integrators and differentiators. So my claim is that the digital low-pass filters, that's what I mean here when I say LPFs, that stands for low-pass filters. The digital low-pass filters that we will look at will look like they are averaging or integrating functions. So they're going to look like these functions that average our signals or integrate them. Previously we saw that high frequencies manifest as sharp edges in time domain signals. So if we apply a low-pass filter to those sharp edges, we will then attenuate those high frequencies, right? If we attenuate high frequencies by low-pass filtering, then we will remove those edges, or equivalently reduce the signal's slope. Okay? So here is an example of a low-pass digital filter. This is a moving average window, which we'll talk about the specifics of in subsequent slides. A moving average window low-pass filter that has been applied to a square wave function, right? So the blue curve here is the square wave input function, and the red curve is what we get if we apply this low-pass filter one time to the signal, and the green curve is what we get if we apply the low-pass filter two times, right? So we have signal filtered once, filtered twice. And what you can see here is that we have, by low-pass filtering, my claim was that we had attenuated the high frequencies of our input signal of the square wave, And we know that in a square wave, we talked about this before in class, that the edges of a square wave contain the high frequencies, right? It's the high frequencies that are required to generate the edges of a square wave. And so by low-pass filtering, we have attenuated those edges, and we have also, in turn, reduced the signal's slope, right? So you can see that we have with the blue input signal, we had an infinite slope. We had an instantaneous jump from 0 to 1, and then an instantaneous jump from 1 to -1, and so on. But we have reduced that slope substantially by low-pass filtering. Now we have these finite lower slopes in the output signal. And here it is blown up so that you can see that, with filtering once, again, we have reduced the signal slope, and with filtering twice, we reduce it further. You can see that also we eventually obtain, with the more filtering we have, the closer the filtered signal is going to come to 0. So we're going to come closer to the mean value of the signal, which is 0, right? The mean value of a square wave is just 0 over time. Okay, so as I just said, as the number of times you filter your signal goes to infinity, right, infinity here, the filtered signal will tend towards 0 in this case, which is equal to the average value of the square wave. As I said, the average value of a square wave is 0, and so low-pass filtering it again and again and again is going to reduce the output signal further and further and further till it tends towards 0. Okay, and so therefore, what we can say about a low-pass filter is that it finds a local average value of an input signal, and it acts as an integrator to frequencies above its cutoff. And we can also think about this in terms of a line. So the average value of a line is its intercept, right? The point at which it intersects the y-axis at x equals 0. So a low-pass filter will reduce the slope of a line towards 0, which would reduce the formerly it was a line. If you reduce a line towards 0, I guess it's still a line, but the slope goes to 0, so it's really just a constant. And it will be reduced to its intercept as you low-pass filter more and more. Okay? Another way to see this is by analogy with Laplace transforms. So the Laplace representation of integration is 1 over s, which is approximately the same as a low-pass filter's transfer function when the frequency is much, much bigger than the cutoff frequency. So I'll write much, much bigger here. So when omega is much, much bigger than omega c, the cutoff frequency. So to see that, I am showing here the transfer function of a single-pole low-pass filter of the type that we've looked at so far. And if we take the limit as omega gets much, much bigger than the cutoff frequency, that is in the stop band, then this guy becomes minus j times omega c over omega, which is equal to omega c over j omega. So you can see that that happens because the imaginary component of the denominator becomes so much bigger than its real component that you can neglect the real component, and then this guy comes out on top, flipped over. Okay, and then we can substitute s, the Laplace variable, for j omega, and get omega c over s, which is just a scaled version of the integration of the Laplace integration function, right? So the Laplace integration function is 1 over s. This is what we apply to a given function, given function's Laplacian, given function's Laplace transform, in order to get the transform of its integral. And we find that here the low-pass filter at very high frequencies has the same form as that integration function. So that's another way to see that low-pass filters act as integrators. Now similarly, if we remove the local average value of a given input signal or its low frequencies, then only the high frequency edges will be left at the output. So this is a depiction of the square wave after high-pass filtering, right? So the original signal looked like this. It would have been positive, and then gone negative, and then gone positive again. So we get a spike at every edge, right? And if we high-pass filter that, then we only preserve the edges of the original signal. And just as in the low-pass filter case, we can draw an analogy with Laplace transforms, in that the Laplace interpretation of this is that, or the Laplace representation of differentiation is just S, which is approximately the same as a high-pass filter's transfer function when omega is much, much less than omega c, when we're talking about frequencies that are much, much less than the cutoff frequency of a high-pass filter. Note that this is opposite the case for the low-pass filter. So, but in both cases, we are interested in the stop band of the filter's transfer function. So here I've written the transfer function of a generic high-pass filter of the type that we've talked about in class so far, of the analog type that we've talked about in class so far. And if we take the limit of this as omega gets much, much, much smaller than omega c, then what we get is j times omega divided by omega c. Right, and that happens because if omega is much, much less than omega c, then the real part of the denominator dominates here, and we can neglect this imaginary part, just leaving the numerator. Okay, and then again, just as in the low-pass filter case, we can substitute S for j omega and obtain S over omega c, which again you can see is a scaled version of the differentiation function. Right, so this is the function that you would apply to the Laplace transform of a given function in order to calculate its derivative, and indeed it turns out that the high-pass filter for frequencies much lower than the cutoff frequency has the same form, so it's doing the same thing. Okay, so now that we've covered that, now let's get into the nitty-gritty of digital low-pass filters. So this very simplest form of a digital low-pass filter is a moving average filter. And let's illustrate this through an example. A moving average filter essentially takes the average of consecutive samples in your signal. So let's say that we have this input signal here, which is given by these discrete samples. These are entries in a vector, for example. So then this is the first entry and this is the last entry. And we want to calculate we want to filter this signal. So each of these represents some number that we have, and we want to calculate the moving filter this signal using a moving average. And so the output would be something like this. Let's say we're using a window width of 3. We'll talk about what that is in just a second. So if we're using a window width of 3, then the output signal would be A plus B plus C divided by 3 for that one. Then we would take the average of the next consecutive 3 samples, and that would give us B plus C plus D over 3. Then we move on to the next consecutive 3 samples, and we would get C plus D plus E over 3, and so on. You can see how this would go as we move on through the signal, how we just continue to take averages of 3 consecutive samples to get the filtered signal. So this output here would be the filtered signal after applying the moving average filter. Okay, so now let's talk about the characteristics and features of a moving average filter. So the most important one to be comfortable with is the window width of the filter. And I'm often going to write that as WW here for shorthand. So this is equal to the number of data points in a moving average window. In the example that we showed on the previous page, or the window width was 3. Moving average filters are probably the easiest filters to implement in code. They're super easy. You just move through your signal and you calculate the average of however many consecutive samples correspond to your window width. The window width is usually set to be odd, and this is simply for interpretation convenience, because if you make it odd, then the window will be centered nicely on a sample of the input time series of the input signal, and it will equally weight past and future values. So that is, it will use the same number of past values as it uses of future values in the moving average calculation. Okay. Another thing to keep in mind about low-pass filters is that, or any low-pass filter, is that it will reduce the number of data points by the window width minus 1 over 2. That is, assuming that the window width is odd. Then it will reduce the number of data points by window width minus 1 over, parentheses, close parentheses, over 2 at each end of your signal vector. Okay, so you're going to lose this many samples at each end, and that's just because the first valid one that we can actually calculate, the first valid output sample that we can actually calculate, has to have at least window width samples in the calculation, and you can't start that until you've gotten to you can't do that right at the first index of the signal. You have to wait until you've gotten to sample window width minus 1 over 2 to do that. Another thing is that as the window width increases, the cutoff frequency will decrease, and we're going to talk about it more specifically exactly what that relationship is later in the next lecture. Sorry, it will decrease. So there is one fairly significant disadvantage of moving average filters compared to other types of digital low-pass filters, and that is that their transfer function isn't particularly sharp. The region between the transition region between the pass band and the stop band is relatively wide compared to other kinds of digital filters. If we put a little bit of effort into optimizing a digital filter, we can do quite a bit better than the moving average. Okay, and the reason for this theoretically, why this transition is so bad, is that a moving average operation is equivalent to convolving an input signal with a rect function whose Fourier transform is a sinc. The Fourier transform of a rect is a sinc. Now that frequency domain function has relatively high side lobes next to the main lobe corresponding to the pass band. So I'll draw that here, draw these functions here. So this is a rect function here on the left, and it's 0 most of the time, but it's 1 for this one short period of time. This is time t, and its Fourier transform is a sinc. And there's frequency and sort of h of j omega of the rect filter, and it is a sinc. Okay? And so what you can see here is that if you were to take the magnitude, of this filter, it would kind of fall off like that as a function of frequency. And you can see that you have these relatively big side lobes here. There's a big side lobe in amplitude, and it turns out then that because of those side lobes, it actually decays relatively slowly as we move up in frequencies. So it moves into the stop band fairly slowly, and it's easy to do a lot better by just a little bit of optimization. But performing that optimization is somewhat beyond the scope of this course, though it's fairly straightforward to do in MATLAB. Okay, but let's say that we have decided to go ahead and stick with the moving average filter for a given application. And we apply it once, and we find, man, that worked okay, but it could be a little bit smoother, So the question that we ask here then is, what if one pass with the filter doesn't smooth enough? You have sort of two options. You could either apply it a different time, redo the operation with a different window width. If you increase the window width, that should decrease the cutoff frequency, and so it should smooth your output signal more. Okay, and we'll talk more specifics about that later. Your other option is to make another pass with the same window width, which is usually the better approach. Okay, and so what that is going to look like is the following. Now let's say, for the purpose of illustration, that we have already filtered our signal once using a window width 3 moving average filter, as we illustrated earlier, and we got these 4 output samples. If we do it again, then essentially we will take these 3 samples of the output and average them to get one sample of the new output, and then we will take these 3 samples to get another sample of the second twice filtered output. Okay, so that would essentially look like this. The first sample, if you work out the weights, you would get this. You would get 1/9 times A plus 2 times B plus 3 times C plus 2 times D plus E. And then this second sample would give you 1/9 times B plus 2C plus 3D plus 2E plus F. Right? So you have the same set of weights that are just applied to different sets of contiguous numbers. Okay, so you can see now that the numbers are weighted differently in the output. So you're effectively applying a little bit different filter here. Now, equivalently, instead of just making a pass with a filter that is essentially all ones, which is what you do in the moving average window, you could instead make a single pass with the filter. Let's see if I can write this cleanly. It'd be 1/9, just collecting those coefficients that we showed on the previous slide, times 1, 2, 3, 2, 1. That would be the filter you would apply instead of the all ones filter that you're effectively applying using the moving average. So just for reference then, the window width, for comparison, the window width 3 moving average would have had these coefficients, 1/3 times 1, 1, 1, just so that you get some context there. Okay, and we can compare these then, of course. If you were to plot them as a function of integer index n, then you essentially you do a stem plot. We often do these stem plots when we're plotting discrete signals. So this is the original filter, which had amplitude 1/3 and then was zeros the rest of the time. That's the original moving average filter. This new one that we have here that we effectively get when we do 2 passes looks like this. Let's see, it has and it comes up to the same amplitude in the middle. It's triangular shaped, right? Okay, so that's a comparison of those 2 filters. You can see that the new filter with 2 window widths is effectively a bit longer, right? We have an extra sample on either side. So here's an example that I cooked up in MATLAB. Essentially what I did was I took this underlying sinusoid function and I added just a ton of noise to it. So the blue line here is the noisy signal. And the red line here is the filtered signal, using 3 different kinds of filters. Okay, so the first filter that I used was a single moving average filter with a window size of 5. And you can start to pick out the sinusoidal kind of shape of the original underlying signal, but it's not all that clear, right? So you say, okay, well, I would like to filter that a bit more. Why don't we do a window size of 9? Okay, but doing a window size of 9 sort of appears to leave actually kind of a lot of the noise-like variations, right? Because the underlying signal appears to have a variation, a sinusoidal variation, kind of like this, right? Whereas any faster squiggles we're saying are noise. And the windows, by increasing the window width, then the WW parameter, that's what I have up here. You can see that not only are we kind of leaving a lot of the noise, but we're actually suppressing a lot of the signal too, unfortunately. And it turns out that the far better approach is to apply the window size 5 twice in succession, which is what we just showed on the previous slide with the case of 3. So if we just extend that a bit and apply it twice, that's what we're doing here. And here you can see that we're doing a bit better job. So this window applied twice here is like the same thing as cascading 2 analog filters. That is, we get a little bit sharper of a transition region between the passband and the stop band, and that better suppresses the noise while sparing the signal. Okay, so here you can see that we do actually get, you can pick out the signal a fair bit better, but the noise is nicely suppressed. And here's a comparison of those filters' transfer functions. So here's note that I've on the y-axis here I've got the magnitude of the transfer functions both in linear, both on a linear plot and a log-log plot. So here's the window size of 5. It's got a relatively higher cutoff frequency. You can see that you have the big side lobes here, giving the relatively smooth overall decay, not particularly sharp. But that if we increase the window size to 9, the window width or window size to 9, then yeah, we decrease the cutoff frequency a fair bit, but we haven't really done anything to decrease the size of the side lobes. On the other hand, if we use a window size of 5 applied twice, we're actually using effectively a different filter. And so we don't compromise the cutoff frequency as much, and the side lobes are much lower. That's why we got that significantly better performance with the window size of 5 applied twice on the previous slide. Here's sort of just showing the same thing on a log-log plot. Now, as I alluded to earlier, there are also some well-known and well-studied algorithms available, such as algorithms that are built into MATLAB that will numerically optimize filter coefficients for you to achieve your desired frequency domain characteristics of your transfer function. And broadly speaking, what these algorithms seek to do is to minimize passband and stopband ripples in your transfer function. Okay, so they seek to minimize passband and stopband ripples, and they also seek to minimize the width of the transition region between the passband and the stopband. So you want that to be as sharp as possible, and you want to have as small of ripples or errors in the passband and stopbands. These filters will generally need to be a fair bit longer than the window widths that we have illustrated here for moving average filters, such as this window width of 5, for example. But let me try to illustrate what I mean by these ripples. So if we plot a transfer function here, see the magnitude of a transfer function as a function of omega of frequency, then we have some region that corresponds to the passband. Then we have some region that corresponds to a transition band, and then we have some region that corresponds to a stop band. So this is the passband, this is the transition region, and this is the stop band. And our filters will always have some squiggle, some error. The actual transfer function will have will squiggle around somewhat between these between some bounds in the passband and stopband. So generally speaking, what we want to do is try to minimize the amplitudes of those squiggles, of those ripples, and at the same time make the transition region between the passband and the stopband as short as possible. And there are functions that are built into MATLAB that will help us do that. And it turns out that regardless of the kind of filter you're trying to use, the longer the filter is, the better it will perform by these metrics. So that is, these metrics of trying to minimize the passband and stopband ripple and make the transition width as narrow as possible. So, and intuitively, that's because the longer the filter is, the better it can approximate a real sinc function, whose Fourier transform, as we saw before, is a rect function. Right? So the ideal transfer function would really be a rect function, since a rect function, as a function of frequency, would have flat ripples, it would have zero ripples, and it would have an instantaneously sharp transition band. Okay, so it would satisfy these metrics of trying to reduce ripples and make the transition region as narrow as possible exactly. The limit to window width is usually the data block size, which in real-time systems is usually kept small. It's usually kept as some, 2 to the 10th or so block size in order to minimize latency. That is the wait time that we have between when we collect the signal and actually get the real-time response, or get some output of that signal. Okay? In non-real-time systems, the limit is usually how many time points we have before and after the interesting parts of the signal. So that is, if we can take all the time points that we have, that we collect in a given experiment, that can often be, milliseconds. So it can be many, thousands or hundreds of thousands of samples. And so there, it's really the only limit to how long of a filter you can use is going to be the amount of time that you have on either end of the signal. Earlier, we alluded to the fact that moving average windows or any other kind of digital filter will chop off samples at the ends of your signal, and so we have to give enough time have enough time in our signal that is uninteresting at the ends, that we don't care about deriving any quantitative information from at the ends of the signal vectors, to be able to throw away so we can use a longer filter. Okay, but generally speaking, the longer the filter, the better the response. So that's it for this lecture. We talked about low-pass filters as integrators. Remember, we talked about these analogies of digital low-pass and high-pass filters. We talked about how you can think of a low-pass filter as being sort of a local integrator or local averager, and whereas high-pass filters act as differentiators. They will actually essentially calculate the derivative of our input signal and emphasize the changes in the signal. We also then talked about the features and use and practical considerations of using moving average window low-pass filters. So next time we will get into a little bit more specifics of low-pass filters, and then we will get into high-pass filters and median filters.